In section 4.6, we're going to combine all of the different methods we talked about so far in this chapter. Things like increasing, decreasing functions, concavity, inflection points, in order to create some really detailed graphs of functions by hand. Some of the guidelines that are given for analyzing the graph of a function is to, first of all, determine the domain and the range. We'll begin by finding the domain. The range we can figure out once we actually have the graph in place. We would also want to do things like find any intercepts where the graph intersects either the x or y axis. Also look for things like asymptotes. And if you notice that the function has like a certain type of symmetry, we can oftentimes exploit symmetry, whether it be symmetry with respect to the y-axis or like a origin symmetry to make the graphing a little bit easier. So these are all of the things that you typically would have done back in like a college algebra class. And then in addition to that, we want to, figure out where's the function increasing, where is it decreasing, where are the relative extrema, etc. Let's take a look at example 1. We want to sketch the graph of f of x equals 2 times x squared minus 9 divided by x squared minus 4. For this graph, let's first of all start with the domain. It does have a denominator, and we know that that denominator cannot be equal to 0 for this to be defined. So it's going to be all x such that x squared minus 4 cannot be equal to 0. That means that x squared cannot be equal to 4. Taking square roots will mean that x cannot be equal to plus or minus 2. So the domain of this function is going to be all x except plus or minus 2. The next thing we're going to do is let's find our intercepts. If you wanted to find the x-intercepts of a graph, you set the function equal to 0 and solve for x. So set f of x equal to 0 and solve for x. If we do this, a fraction is going to ever be equal to 0 whenever the numerator is 0. So I'm just going to do the shortcut of setting the numerator equal to 0. Divide both sides by 2. We get x squared minus 9 equals 0. Add 9 to both sides and then take the square root. We would get 2 intercepts, x equals plus or minus 3. So for this graph, our x-intercepts are going to be negative 3, 0, and then also 3, 0. We will now go ahead and find our y-intercept. To find the y-intercept, you just evaluate f of 0. So different style procedure, this is an evaluation. If we plug 0 into the function, we would get f of 0 would be equal to 2 times 0 squared minus 9 divided by 0 squared minus 4. This is going to be negative 18 over negative 4, which would be positive 9 halves, or 4.5. So when x is 0, the y-coordinate would be 9 halves. That gives us our intercepts. We now also want to look for our asymptotes. This is a rational function, so we should be able to highlight those pretty easily. For the vertical asymptotes, those would be any values of x would make the denominator equal to 0, but not also simultaneously the numerator equal to 0. We solved for those a moment ago, but it turns out it's going to have a vertical asymptote at both positive 2 and a negative 2. We can check. We know that they make the denominator 0, and if you plug them into the numerator, those would make the numerator non-zero, so they do end up being a vertical asymptote. For the horizontal asymptote, because it's a rational function, we can compare the highest powers of x in the numerator and denominator. Be a little bit careful because of that factorization. The numerator would really look like 2x squared minus 18. The denominator is x squared minus 4. Numerator and denominator both have the same highest power of x. So the horizontal asymptote should be y equals the ratio of those leading coefficients, which would be y equals to 2. So let's just kind of categorize everything we have at the moment. So we know we have vertical asymptotes at plus or minus 2. We know that we have some x-intercepts, negative 3 comma 0, positive 3 comma 0, and then also 0 comma 9 halves. The next thing we're going to do is let's go ahead and take the derivative in order to find where this function is going to be increasing, decreasing, and also to look for relative extrema. So let's go ahead and do this. To find the derivative, first of all, I can use the constant multiple rule. We have that 2 that's a factor in the numerator. Just bring that 2 out in front as a constant multiple. The quotient rule says we would do the derivative of the numerator. That's going to be 2x times the denominator minus the numerator times the derivative of the denominator. That'd be 2x. And then all over that denominator squared. X squared minus 4 squared. From here, we would like to try to go ahead and simplify this. Easiest way is to factor out any common factors from the numerator. Notice that both of these terms have a common factor of 2x. So I can factor that 2x out, multiply it by the 2 that's already in front, and I would get 4x with the following. It's going to be x squared minus 4, but then I have to subtract x squared minus 9. So that would become x squared minus 4 minus x squared plus 9, all divided by x squared minus 4 squared. F prime of x is equal to, notice that in the numerator, the positive x squared and the negative x squared cancel. We have negative 4 plus 9, which would be 5. 4x times 5 would be 20x. All divided by x squared minus 4 squared. So we have our derivative. The next thing we're going to look for is our critical numbers. The critical numbers are going to be where f prime of x is equal to 0. This fraction will be equal to 0 precisely when the numerator is 0, which occurs when x equals to 0. We also will have some places where f prime of x is undefined. When we set the denominator equal to 0, x squared minus 4 squared will be equal to 0. You can take a square root, bring the 4 over and take a square root again, and this would produce x equals plus or minus 2. Those are the points that we saw earlier where this graph is going to have vertical asymptotes. We can now go ahead and do a sign chart to see the intervals of increase and decrease for f prime. So negative 2, 0, and 2. Those three numbers will break the number line up into 1, 2, 3, 4 different regions. We would want to go ahead and pick a test point within each region. For example, in region 1, the test point x equals to negative 3 would work nicely. And then you would go ahead and plug that into the derivative. F prime of negative 3, that would be 20 times negative 3, all divided by negative 3 squared minus 4 squared, which is going to give us negative 60 all over. Negative 3 squared is 9. 9 minus 4 is 5. And then 5 squared is 25. So we get negative 60 over 25, which is less than 0. So that tells us that in this region here, f prime is less than 0, so the function is decreasing. We also want to keep in mind that here and here we have vertical asymptotes. So let me write those points as open circles. we now want to test the derivative in each of the remaining 3 regions. In region 2, a good test point to use would be x equals to -1. And I'll skip some of this arithmetic. But if you look at the form of f prime, very quickly we see that the denominator, because it's being raised to a second power, that denominator is always going to be positive. So the sign of the derivative will be entirely dictated by the sign of the numerator, which is 20x, and that's just the same thing as the sign of x. So it will turn out that in region 2, if you were to work this out, in region 2, the derivative is also going to be less than 0, so it's decreasing here. In region 3, it's going to be increasing. If you use the test point, for example, use the test point x equals to 1, plug it into f prime, you should see f prime will be positive. So it's increasing here. And then in region 4, it will again be increasing. So we now know where f is increasing at. So it's increasing on 0 to 2, and then from 2 to infinity. It's decreasing from -infinity to -2, and also from -2 to 0. And one of the other things that we've seen here is that at that critical number 0, the function changes from decreasing to increasing, so we actually have a relative min at x equals to 0. At that point, you would want to plug 0 into the function, and we already did this before. We already plugged 0 in. That turned out to be the y-intercept. So the y-intercept here, the order pair 0, 9/2, is a relative min. So we have all of that good information. The next thing we're going to go ahead and do is we want to find our second derivative so we can investigate concavity and also potential inflection points. So let me just kind of go ahead and clear off all of the stuff except for the first derivative. We said that f prime of x was equal to 20x all over x squared minus 4 squared. And now we're going to go ahead and take the second derivative. To do the second derivative, I'm going to again use the constant multiple rule. Let me just kind of bring that 20 out in front. I'm thinking of the numerator as x. I'm thinking of the denominator as x squared minus 4 quantity squared. The derivative of the numerator would be 1 times the denominator minus the numerator, which I'm thinking of as x right now, times the derivative of the denominator, which will require the chain rule. This is going to be 2, leave the inside alone, bring the power down by 1, and then from the chain rule, we need to multiply by the derivative of the inside. The derivative of x squared minus 4, well, that's going to be 2x all over that original denominator squared. So it's x squared minus 4 squared squared. We now want to go ahead and simplify the second derivative. F double prime of x is equal to, and the way we're going to simplify this is by, again, pulling out common factors. We have this 20 up top. The denominator is going to be x squared minus 4 to the 4th power. In the numerator, we have this. We have x squared minus 4 squared minus an x times 2 times 2 times x is going to be 4x squared times x squared minus 4. And both terms in the numerator have a common factor of x squared minus 4, so we can pull that out. Let's factor it out. We get 20 times x squared minus 4 times x squared minus 4 minus 4x squared, all divided by x squared minus 4 to the fourth. We can cancel one power of this factor that's from the numerator with one of the powers that's in the denominator. F double prime of x is equal to, we still have the 20 out in front. On the inside, this will simplify. X squared minus 4x squared. That will end up being a negative 3x squared minus 4 all over x squared minus 4 to the third power. Okay. So a little bit of arithmetic, but we now have our second derivative. F double prime of x is equal to 20 times negative 3x squared minus 4 all over x squared minus 4 cubed. Now I'm going to do one more thing just because it's going to make some computations easier for me because I'm not going to plug this stuff into my calculator. There's a common factor of a negative 1 in that numerator. I'm going to go ahead and just bring that out. So I can make both of these positive if I just kind of put that negative out in front. Okay, so what do we want to do next? We want to see if we can find any places where the second derivative is undefined or equal to 0. Well, the solutions to where it's undefined are the same we've seen a bunch now. Set the denominator equal to 0. That will once again produce the plus or minus 2. If we were looking for where the second derivative is equal to 0, well, that's where the numerator is going to be equal to 0. That's negative 20 times 3x squared plus 4. Where is this equal to 0? Divide both sides by negative 20. We get 3x squared plus 4 equals to 0. Subtract 4 from both sides. Divide by 3. And now we have x squared equals negative 4/3. When we take the square root, those are going to provide two complex solutions. We're only interested in real solutions right now, so there's no real numbers for which the second derivative will be equal to 0. Let's now go ahead then and do our sign chart for the second derivative. That'll tell us about the concavity. So we have two numbers here, negative 2 and positive 2. Those corresponding to our vertical asymptotes of our original function. Those two numbers break the number line up into three regions. Region 1, Region 2, Region 3. And we want to go ahead and see if we can check the sign of the second derivative within each region. For example, in Region 1, I might use the test point x equals to negative 3. F double prime of negative 3 would be equal to negative 20 times 3 times negative 3 squared plus 4, all divided by negative 3 squared minus 4 cubed. Negative 3 squared is 9. 9 times 3 is 27. 27 plus 4 is 31. Times that by negative 20. That's going to give us a negative 620 in the numerator. All divided by, in the denominator, negative 3 squared is 9. 9 minus 4 is 5. And then 5 cubed would be 125. So in the first region, we see that the second derivative is less than 0. And when the second derivative is less than 0, that means the graph is going to be concave down. So it's concave down in region 1. I'll leave it up to you to check these on your own, but a great test point in region 2 would be 0. If you plug 0 into the second derivative, what you should find is the f double prime of 0 is going to be positive. And if the second derivative is positive, then the graph is going to be concave up. And then use a test point, let's say x equals to 3, you would see that the graph will be concave down there as well. At x equals to 3, the second derivative should be negative, so the graph's going to be concave down there as well. Okay. Notice, however, even though we do have a change in concavity, these are not going to be inflection points because -2 and 2 are not in the domain of our function. Had those two values been in the domain of the function, then they would have been inflection points, and you should have plugged them into the function to see what the ordered pairs would be in the function values. Okay. So let's highlight this. The graph we said was going to be concave up between -2 and 2, and it's going to be concave down from -infinity to -2, and also from 2 to infinity. With all of this information, we should be able to now go ahead and draw a pretty accurate graph of this function. Okay. Whenever you're doing your function graphs, you always want to begin by plotting any points as well as any asymptotes that you have. We know we have a y-intercept. Maybe I'll do the graph in green. At 0, 9/2, that's 0, 4.5. That's going to be about here. We have a y-intercept at -3 and +3. We also have some asymptotes. We have a vertical asymptote at x equals -2. Vertical asymptote at x equals to +2. And we also had a horizontal asymptote at y equals to 2. From here, we know that the function was decreasing on -infinity to -2, and it's concave down has to follow the asymptotes, so it's going to look like this. We also know that it's concave up between -2 and +2. It is decreasing where is it? From -2 to 0. So it's decreasing like this, and then from 0 to 2 it's increasing. And just as we said, that creates our relative minimum at that order pair 0, 9/2. And then for x greater than 2, the graph is increasing, and it once again should be concave down. So putting that all together, first derivative test, second derivative sign charts, we can find relative extrema, we can find our inflection point, our concavity. Combining that with our pre-calculus things like intercepts and asymptotes allows us to draw a very accurate graph of these things by hand.